All right, everyone, we are back and we are going to go through our solution, or excuse me, I'm in problem set solution mode. We're going to talk about air. So, air is really, really critical when we're thinking about a measurements and instrumentation course. We have to quantify whenever we actually finally get a measurand, what's the uncertainty associated with that measurement. So, you're never going to give me a single value. Instead, there's always going to be an upper and lower bound. We're going to have to quantify essentially the uncertainty. We're going to talk about different types of air in just a bit, but we are really, really focused on that. We have to be able to quantify essentially those values. So when we're thinking about uncertainty and we're thinking about air, one of the things we have to kind of figure out, again, tolerances, you all know that from manufacturing, all of that good stuff. But we need to know and use correct terminology when we're assessing essentially the measurements. So accuracy, when we say something is accurate, we're basically, even though we've kind of gone on this diatribe of like true value, measured values, it's basically what's the difference. If I have something that's highly accurate, the measured and the true or the theoretical value or what you expect, it's going to be very, very small, that difference. So the closer that we are from the measured and true, more accurate. Precision has nothing to do with accuracy. It's just the difference between the reported values during the same measurement. So basically, if I'm able to measure something consistently, meaning I get 148.9 Kelvin, 148.8, 140, again, if I'm repeatedly measuring things and the difference between those values is very, very small, I have high precision. Resolution is essentially related to your measurement apparatus, your tool. So it's the smallest incremental change that you can measure by your readout scale. So for example, a micrometer has a higher resolution than a yardstick because I can measure something on the orders of micrometers. Yardstick, really a yard or half a yard, that order of magnitude, that kind of scale. Sensitivity is usually related to kind of precision and resolution, and especially resolution. It's just the change in the output per unit change in the measured quantity. So if I have something with high resolution, high sensitivity, but make sure we're using those words correctly. So when we're looking at uncertainty, when we're looking at air, I'll often hear, and these are lots of kind of piece of advice on how do you deal with air and uncertainty, looking at bias and precision air. We're going to talk about this in just a bit, but I hear these phrases a lot when we're in the lab. How good is your data? How well does your experimental data fit theory? What's the R squared value? What's the percent air? These are well-intentioned questions, and it's good that you're thinking about these things, but these are horrible questions. How good is your data? What do you mean by that? Are you talking about accuracy, precision, uncertainty, how well it's matching theory? Again, good is not essentially a terminology. And if you get an unexpected result, that's actually great as long as everything else you're doing in the lab is correct and consistent and it's not basically illegitimate error. So we have to be more precise and clear in terms of our language when we're assessing essentially our data. So how good is your data? What do you mean by that? You have to expand upon that. How well does your experimental data fit the theory? This could be a good question if you're seeking to do this in a lab, right? Like if you're seeking to reproduce other experiments, that's a good idea. But if you're searching for something and you're doing new and novel experiments, you may find something new, and then you have to kind of decide, is the theory that you're trying to match applicable to your situation? R squared values. I could have a data set that looks like this, and I can say I can fit a 12th order polynomial in Excel, although you'll never plot in Excel because we're engineers, we don't use Excel. We're beyond that. I can do a 12th order polynomial and I can get an R squared value that's 0.99. But a 12th order polynomial is not going to describe a real physical world situation. Instead, you might have a best fit where the R squared is equal to 0.9. That is the better fit. So you need to justify and explain. It's not just about, you should not be worried, and you should, it's really, I think, silly to focus on that R squared value as the beginning and end of your error analysis. So we're not going to do that much at all in this class. And finally, percent error. So basically like your measured minus true over true. You will times 100. You please you will never do that in this course. So we're moving beyond that. So we need to make sure, and what we're going to instead do, we are going to quantify air. Basically, although we just said we're not going to do measure minus true, but this is kind of the rough idea. But there are multiple different types of air. Precision air, bias air, illegitimate, and airs that are sometimes biased, sometimes precision. So precision air will have basically a distribution. Sometimes it's called random error. I don't like that terminology. So precision error is the one we're going to use most often. You can say stochastic error, but basically you can imagine precision error is like disturbances or fluctuations to the equipment. So if you see like on your scale, so if I have a scale or if I'm doing a microbalance and I'm reading essentially the measurement on that scale, 1.345 milligrams, and this number keeps fluctuating, or some of these measurements keep fluctuating, or I have multiple samples and they look pretty similar, but there's some differences between them. I'm putting them on and there's different measurements each time. Those are precision errors. They have a distribution. So if this is the true value here, and this is your measured value, the distribution of those measurements, they'll have basically, or that error will have some type of distribution. So it floats left again. So it's you need to have a statistical toolkit to deal with this types of error. So it could be temperature fluctuating in a room when you're doing a thermocouple measurement. It could be length of the beam. You can get slightly different measurements each time, et cetera, et cetera. Bias or systematic errors, those are related again kind of to the resolution, and it's basically errors that are going to occur the same way each time. So on that scale example, let's just say that I bought a scale, and for some reason it's just always, my scale in particular, it's always a kilogram heavier than what I actually weigh. I'm just kidding. Although I wish that's my justification, but anyways, so it's basically, you can kind of think about it like a calibration error, right? Or if you're doing an experiment where, for example, you're let's say you're having someone that has a stopwatch timing voltage measurements, someone who's kind of consistently a little bit fast or a little bit slow. Defective equipment, this could be illegitimate error, but loading errors, not putting it directly in the center, system resolution limits. So there's a resolution, that scale example, the fluctuating, number, that could also be a bias error as well. If your system can't measure those values. So bias error and precision error are the key sources of error that we are going to analyze. Illegitimate error is another type of error. So when you make a mistake during an experiment, when you do a calculation error, when you're doing an analysis incorrectly, these are not errors you will ever discuss in a lab report. You must redo the experiment if you do any type of illegitimate error. Those should not be reported. You have to do the experiment again. There are also errors that can be sometimes bias and sometimes precision. It's kind of a philosophical argument about which is which. But as long as you perform the analysis consistently and you discuss that, you should be in good shape. So the total uncertainty will always just be basically the square root of your bias error of that measurand x plus the precision error of the measurand x squared. So again, this is a really critical kind of idea. Precision error will come when you have repeated sample experiments. Most of the time, you'll do this type of experiment. Sometimes you'll do a single sample experiment. That could be if the phenomenon you're trying to see is really expensive to try to reproduce, like the Large Hadron Collider, they're not going to run multiple experiments of that. It could be resource limited. There could be reasons why you do a single sample experiment. You still have to do error analysis there. Most of it will probably come from bias error and some propagation of those errors. But repeated sample experiments are the ones you're going to deal with most. And again, precision is critical here. So how do we capture, how do we start to analyze essentially that type of precision error, this type of like distribution? I've kind of hinted at it before. So we're going to get into that next time when we talk about our Gaussian and normal distributions and how do we calculate confidence intervals, and then how do we calculate essentially measurements and determine uncertainty. So we'll see you all in the next video. Thanks. Bye.